we see that's going to repeat. Now, let's go back to our circle. So let's say we have a wheel, okay, and this wheel is spinning at a constant angular velocity, omega, okay, and there's a ball on this wheel. There's a ball on this wheel, and so the ball, we can say, is going at a certain speed v, and we know that there's a relationship between the tangential speed and the angular speed. It's based on the radius of the wheel, so v equals r times omega, okay? And then there's going to be a light above the wheel, and it shines the light onto the wheel, specifically the ball on the wheel, and it casts a shadow of the ball on the floor. So here's the floor. So right now, the shadow is right here. And then as it travels, so in a quarter of a period, it's going to be right here. And then the shadow is right here. And then half a period of time, our ball is here, and our shadow is here. And then 3/4 of a period,
right under it.
the ball is here, but the shadow is back in the middle position. And then a full pi of rotation here, and we're back to the same spot, and our shadow is back to the same spot. So as we track this, look at what happens as the ball moves in a circle. Watch what happens to the shadow. As the ball moves in a circle, the shadow moves back and forth, oscillating, just like a mass on a spring.
I'm sorry.
Shadows.
So there's a relationship between uniform circular motion and simple harmonic motion. We'll learn more about that relationship and how the equations work together next class. But if we look at our first equation here, so we've already learned about the period, the time for one complete cycle. So the time it takes for that ball to go around once is going to be the same time as the shadow moves there and back. One full oscillation, it's the same time. And we know that the time that the period is the inverse of the frequency. Remember, the period means the time for one complete cycle. The frequency is the number of cycles in 1 second. So it's exactly inverse of each other. And then, of course, it is related to the angular speed, but in oscillations, we're actually going to call that angular frequency because angular speed really has no meaning if it's just 1D motion. So we're going to call this angular frequency, but it's the same as the angular speed or the angular velocity from the uniform circular motion. Same letter, and it means the same thing. We're just going to call it two different things. Just like we called the acceleration due to gravity also the gravitational field strength. They are the same thing, just different ways of looking at it. Okay, good. Now let's take a look at our mass on a spring. More importantly, notice that the amplitude, or how far I displace it, there's no x in the equation. So it doesn't matter how much I compress or stretch, like if I were to go to this example here, notice that they're still oscillating, but they're not oscillating with the same amplitude that they were before. They've kind of decreased the energy, but the time it takes to go one full cycle hasn't changed, okay? The period here is going to be the same period as it is with a large amplitude. The time for one complete oscillation is the same. So the amplitude doesn't have any bearing on the rate of oscillation, on the period, or the frequency, okay? But what does is the mass and the spring constant. So let's refresh our memories about how to find our spring constant. We have two different springs here. I have two same masses. So I'm going to put these masses on the spring. So each of them is going to experience the same force. So my question is, which one has a higher spring constant? Let's choose our first one to be A. So here's A. It stretches about that big. And then this is spring B. It stretches about that big. So remember how we found our spring constant.
Wait.
Our force equation, our Hooke's law, F equals kx. So if we're looking for our spring constant, force divided by x, when we look at this and we're trying to find out which one has the higher spring constant, which one, is it A or B?
A. I think.
A does, yeah. Notice that the force acting on both of them are the same, because I have the same mass pulling down. So the only thing that can change is our displacement. And notice there's an inverse relationship because x is on the bottom of the fraction. So with more displacement here in B gives us less spring constant because they're inverse. So to answer our question, if we want more spring constant, we have to choose the one that has the less displacement, which would be A. So now notice that now we know which one has the spring constant. So this one has a larger spring constant. Notice the period equation, K is again on the bottom of the fraction. So again, there's an inverse relationship. So what should we expect from the period of a larger spring constant? Less time. And less time means that it oscillates faster. The frequency is greater because there's less time per oscillation. So we can see that it oscillates, like 2 times per second, whereas this one has a lower spring constant. It oscillates like 1 time per second. So the larger our spring constant, the smaller our period, but the larger our frequency. It oscillates quicker if we have more spring constant. But now, let's take a look at our mass. So if we increase the mass, what should happen with our period? It should increase. And if the period increases, what happens to the rate of oscillation or the frequency?
Decreases.
What did you say? So if the period increases, what happens to the frequency?
Decreases.
It has to decrease because they're inverse, okay? So look at this one here, okay? And we're gonna add another mass to it.
Because the frequency is less.
It's gonna stretch down
The
more.
period has
Okay.
to go up. Because they're inverse. So look at the first equation.
Well, the table isn't helping. But you can see that it's oscillating slower now. It takes more time to oscillate, which makes sense because the mass is on the top of the fraction. So as we have more mass, we've got more time, and more time means less frequency. It oscillates fewer cycles per second than it did before. Good, good, good. All right, and then last thing is for the pendulum. Notice again that the amplitude has no bearing on the pendulum. It doesn't matter if I swing it wide or just a little bit. The time is not affected by the amplitude or how far I stretch it out. Okay, but it is dependent on the length and g. So let's take a look. I can easily change my length. Notice how quickly it oscillates, or the rate of oscillation. What should happen as I decrease my length?
Time decreases.
As I decrease my length,
The time decreases.
Period increases?
the period would what?
Decrease.
Would decrease, which means that it should oscillate
right. Faster.
faster. All right?
Yeah, I got confused.
Were you right?
Yeah.
Yeah! Look at that!
So the period
Hell
decreases.
yeah, brother.
Awesome.
So the period
Again,
decreases when?
because
And also it's
the length is direct, or the length has a direct relationship to the period, so the longer it is, the more time it takes to swing back and forth, but the shorter it is, the smaller the time, but the greater the frequency. G, we can't really play with G a whole lot here on the Earth, but if I were to take it to the moon, where the G is less, what would happen to the frequency here? If G is less, what happens to the period?
Increases.
The period would increase, and if the period increases, what happens to the frequency?
Decreases.
The frequency would decrease. So it would oscillate slower on the moon. Okay? What if we put this thing in an elevator and artificially change the G that it feels?
It's like 2D.
Just like we've talked about before, right? So the acceleration that we experience, we feel lighter or heavier because there's an extra acceleration here, okay? So if we put a pendulum in an elevator and we have it accelerating upward, we should feel how? We should feel heavy, right? So what is that going to do to the effective G here?
Increase the G.
It's going to increase.
So decrease the time.
So if the G increases, what happens to the period?
Decreases.
Period decreases, and what happens to the frequency?
Increases.
The frequency increases. So with upward acceleration, how is it going to oscillate?
Faster.
It's going to oscillate faster. And vice versa. If we have acceleration down, we feel lighter, right? So if we feel lighter, that means that the effective G that the pendulum experiences is smaller. With the smaller G, gives you a larger time of the impact, larger time for the oscillation, and more time means slower frequency. So it oscillates slower as we accelerate downward. Cool. All right. That's it, guys. Yeah. Cool stuff. So we've got our pods, we have our quiz, it's live and focused, so if you want to jump straight into that, you are more than welcome to do so. We still have a good chunk of time. We've got 15 minutes before we have to start our test, but I figure I'd just go ahead and open it up for those of you who need to take it. And of course, our retest, if you wanted to take that as well, we'll start right at 2:25. All right, so feel free to take a break before you jump into your work. And let me know if you have any questions. Oh, if you didn't finish your labs, I would like those today, please.
That's not us.
Thank you.
That's not us, right?
What do you mean?
We finished all our labs.
No.
What you mean?
I'm kidding.
Us?